EEE EC 201 Electrical Circuits 1. In today's lecture, we will study the delta Y transformation. Electrical networks can be classified into two types. One having the series parallel configuration and the other having a complex configuration. Networks with series parallel configuration have the resistors connected either in series or in parallel. However, in complex networks, the resistors are not connected in series or parallel. Thus, to solve or analyze this type of complex configurations, there are different techniques available. Node, mesh, delta Y conversion are some of the few techniques which are used to solve this kind of networks. We have already studied node and mesh analysis in the previous lectures. In today's lecture, we will study how we can change one form into another, that is, the Y form, which looks like this, into a del form or vice versa. It is very important to realize that when we change one form of resistance or connection into another form, we are not changing the total resistance. We are just changing the design of the network. The Y configuration will look something like this. There will be three resistors connected in the Y shape. A delta connection will look like this. Also, three resistors connected in this form. The Y and delta configurations are sometimes known as the T and pi connections respectively. In the next few slides, we'll see how we can change one form to the other. These two forms are interchangeable. That is, it is possible to change the delta network to the Y network or the other way around, that is, the Y network into a delta network. The resistors in the delta network, which is this one, are represented by the symbol RA, RB and RC, whereas the resistors in the Y network are represented by the symbols R1, R2 and R3. In order to change the configuration from delta to Y, these are the equations which we will need. To determine R1, the formula which we will need is this one. That is, R1 will be equal to RB multiplied by RC divided by the summation of all the three resistors of the delta network, that is RA plus RB plus RC. RA plus RB plus RC. When we determine the value of R2, it is equal to RC times RA, RA times RC divided by the summation of all three resistors of the delta network. When we determine R3, it is equal to RB times RA, RB times RA divided by the summation of all the three resistors of the delta network. So, as you can see, to determine R1, R2 and R3, the denominators are same in all three expressions. Only the value of the numerator changes. While determining R1, the value of the numerator will be RB times RC. While determining R2, the value of the numerator will be RC times RA. And while determining R3, the value of the numerator will be RB times RA. The denominator remains same in all three equations. In order to transform from Y configuration to delta configuration, these are the three equations which we will need. If you observe carefully, in all three equations, the numerator is the same. That is, the numerator will be equal to R1 times R2 plus R1 times R3 plus R2 times R3. The only change is the value of the denominator. So, when we determine RA, the Y resistor, the resistor in the Y configuration which is opposite to RA is R1. Hence, the denominator is R1. When we determine RB, the resistance in the Y configuration opposite to RB is R2. Thus, we divide the numerator with R2. When we determine RC, the resistor in the Y configuration opposite to RC is R3. Hence, we divide the numerator with R3. In this example, we have to determine the total resistance RT between these two terminals for the following complex configuration. If you look carefully, 4 ohm, 2 ohm and 6 ohm forms one delta configuration. Also, 3 ohm, 3 ohm and 6 ohm creates another delta configuration. In order to solve this network, you can choose any of these delta configurations. In the given solution, the latter delta configuration, that is the one forming with 3 ohm, 3 ohm and 6 ohm has been used. So, using the formulas which we have discussed in the previous slides, this delta configuration has been converted to a Y configuration. The values of R1, R2 and R3 are as follows. Now, since we know the values of R1, R2 and R3, thus if we redraw this network and replace the del connection with a Y configuration, then this is how the network will look. Now we can easily determine RT because the complex configuration has been replaced with its equivalent simple configuration. Now 4 ohm and 1.5 ohm are in series. 2 ohm, 1.5 ohm are in series. Then 5.5 ohm and 3.5 ohm are in parallel. Then that entire section is in series with R3, which is 0.75 ohm. Thus, we can easily determine RT, which is equal to 2.89 ohm. In this example, the complex network has one delta configuration and a Y configuration. So, in order to determine the total resistance RT, we need to convert either this delta configuration into a Y configuration, or we have to convert this Y configuration into a delta configuration. In either case, the value of RT, that is the total resistance of the network, will be equal. So, using the given expressions or the given equations, at first we have converted this del configuration into a Y configuration. And in doing so, the value of R1, R2 and R3 will be equal to 2 ohm. So, if we convert the delta configuration into a Y configuration, then the value of R1, R2 and R3 will be 2 ohm. So, the redrawn network will look something like this. And the value of RT will be equal to 3.27 ohm. On the other hand, if we convert the Y configuration to a del configuration using the given equations, then the value of RA, RB and RC will be equal to 27 ohm. On redrawing the network, it will look something like this. If we determine the value of RT using this format, then you will see that the value of RT in both the cases is equal to 3.27 ohm. This is the end of this lecture. Thank you.